The night was cold on the southern coast of England on 6 June 1944. Hours after the first waves of the Normandy landings, a temporary field hospital near Portsmouth was overflowing with wounded. Stretchers jammed the corridors, nurses yelled for blankets. A corporal from the Royal Engineers sprinted through the rain, shouting the same desperate order again and again. "Get more huts up now!" Within minutes, trucks screeched into position. Steel ribs clattered onto the mud. Corrugated sheets slid off the back of lorries. Lanterns flickered against curved metal as teams of exhausted engineers worked with a speed that looked impossible. They weren't building tents. They weren't building barracks. They were raising something Britain had perfected through decades of war: the Nissen hut. By dawn, wounded soldiers were lying inside brand-new shelters that hadn't existed the night before. But on the other side of the Channel and across the Pacific, the Americans were racing to do the same thing. Their version looked similar: the Quonset hut, the curved steel, the wooden ends, the arching silhouette. But those American huts often took longer to erect, needed different parts, and demanded more from logistics crews. Why? Why could the British assemble their Nissen huts faster, sometimes hours faster, even though America had more factories, more manpower, and more steel? To answer that, we have to go back nearly 3 decades, to a muddy test field in France, and to a man who had no idea he was about to design the most important temporary building of the 20th century. The story began long before World War II on a cold, windswept ridge in northern France in April 1916. The Western Front was drowning in mud. Artillery thundered day and night, and the British Army faced a problem no amount of courage could solve. There simply weren't enough shelters. Not for the men, not for the supplies, not for the medical stations struggling to keep wounded. Soldiers alive. Captain Peter Norman Nissen, a Royal Engineer and former mining engineer, walked through a cluster of soaked canvas tents that sagged under the weight of spring rain. He watched exhausted soldiers scoop water out of their sleeping quarters with helmets. The tents flapped, leaked, and collapsed, and every minute spent fixing them was a minute not spent preparing for battle. Nissen understood structures. He'd worked in mines where cheap, quick support frames often meant the difference between life and death. As he stood in the mud, he lifted a sheet of corrugated steel, lighter than timber, easier to move and resistant to rot, and curved it over an improvised frame. A simple idea sparked. A roof that didn't need complex carpentry. A shelter that could be shipped to the front in pieces and erected by men with no building experience. A hut that used geometry. A perfect arch to distribute its weight and resist the wind. Over the next few weeks, Nissen built his first prototype. The structure curved like a half-cylinder on the ground, steel sheeting over a skeleton of simple arched ribs bolted onto base plates. End walls could be made from whatever was available: wood brick, even sandbags. Inside it stayed warmer than tents, cooler in sunlight, and drier during rain. By summer of 1916, the British Army approved his design. By 1917, they were producing thousands. By the end of the First World War, more than 100,000 Nissen huts had been scattered across Europe. The design wasn't perfect, but it was revolutionary, cheap to ship, simple to build, and durable under fire. And although the First World War ended, the Nissen hut didn't vanish. It sat quietly in engineering manuals and forgotten depots waiting for another global conflict that would demand rapid shelter on a scale no one had ever imagined. When that moment arrived in 1939, Britain already had more than 20 years of experience with a design few armies could match. When Britain entered the Second World War in September 1939, the country faced the same urgent need it had during the First World War, but on a far larger scale. Millions of troops needed shelter. Airfields needed workshops, ports needed storage, medical units needed clean, dry spaces to treat the wounded, and Britain needed all of it fast. The nation turned back to the design that had already proven itself under fire: the Nissen hut. But this time, it wasn't a prototype or an experimental shelter. It was a mature design with decades of refinement behind it. What made the British version so fast was not just the shape or the steel or the tools, it was the system. A system honed between the wars by engineers who had learned that speed was the real secret weapon. By the mid-1930s, the Royal Engineers had standardized nearly every part of the Nissen hut. Sheets came in predictable sizes. Curved ribs were identical arch pieces punched by simple dies. Bolt patterns were uniform. A team of trained soldiers could look at any pile of components and instantly know which piece belonged where. Nothing was left to guesswork. Britain also understood the importance of materials. Timber was rationed, brick was slow, and concrete demanded labour Britain didn't have. But corrugated steel, light, thin, and stackable, could be produced in large quantities and shipped anywhere in the empire. That meant local factories from Canada to India could manufacture compatible pieces without waiting for shipments from London. The army built its own doctrine around the hut. Manuals explained everything from how to unload the trucks to where to place lamps for night construction. Teams practiced erecting huts the way infantry practiced rifle drills. In some units, the Nissen became a competitive task. How fast can your squad raise a full-size hut? A well-trained British crew of 6 could often erect a standard Nissen in under 4 hours. Under ideal conditions, no wind, firm ground, parts sorted beforehand. Some engineers claimed they could finish in less than 2. No fancy cranes, no heavy machinery. Just muscle discipline and a design that didn't need anything more complicated than a ladder, a spanner, and a willingness to work in the rain. By the time the Blitz struck in 1940, Nissen huts were already serving as factory workshops, living quarters for anti-aircraft crews, makeshift classrooms, aircraft hangars, radar stations, and even entire military camps built. From nothing but rows and rows of curved steel. Britain wasn't simply building huts, it was building infrastructure at the speed of war. And when the Americans entered the conflict, they took one look at the Nissen and decided they needed something like it fast. But when they tried to build one of their own, they discovered something surprising. Copying a design isn't the same as inheriting 20 years of experience. When the United States entered the war, after 7th December 1941, the nation faced a logistical nightmare of unprecedented scale. The U.S. military needed instant bases, not just in one region, but across the Atlantic, the Pacific, the Caribbean, and the Arctic. They needed barracks, warehouses, hospitals, command posts, machine shops, and supply depots. And they needed all of it shipped by sea, assembled by untrained crews, and functional within days of landing. The U.S. Navy tried tents. They tried wooden sheds. They tried tar paper shacks. None of them survived long-distance shipping, tropical humidity, Pacific winds, or the brutal requirements of mobile warfare. So the Navy turned to a company known for doing the impossible, George A. Fuller Construction, the firm that had built skyscrapers and naval facilities with industrial precision. Their task was simple on paper and impossible in reality. Create a building that ships flat, assembles fast, and works anywhere in the world. Designers studied the British Nissen hut carefully. The shape was nearly perfect, the arch was strong, the curve shed wind, and the corrugated surface resisted weather. But the Americans didn't want to simply reproduce what the British had spent 2 decades mastering. They wanted a hut tailored for mass production, global shipping, and the wildly mixed environments American forces were about to enter. Within weeks, a prototype rose at Quonset Point Naval Air Station in Rhode Island. The Americans called it the Quonset hut. At first glance, it looked incredibly similar to the Nissen. Same curved silhouette, same ribbed steel, same wooden end walls. But behind those similarities, the U.S. Navy had made a handful of crucial changes, some brilliant, some burdensome. Instead of relying on a frame of simple steel arches, the Americans used larger, deeper, corrugated panels designed to act as both skin and structure. This stressed skin approach meant fewer ribs, but it also required heavy-gauge steel sheets and more robust manufacturing tools. The goal was to reduce the number of unique components. The result was a set of much larger, heavier pieces. The Navy also insisted that the hut be adaptable to cold climates where insulation mattered. So early Quonsets included a complex interior layer of insulation, vapor barriers, and wallboard, useful in Alaska, slower in the jungles of Guadalcanal. America's industrial might made production fast, shockingly fast. By mid-1942, Fuller Construction was producing Quonset components by the trainload. Factories across the country stopped making peacetime products and shifted to rolling sheet steel for huts destined for the Pacific. But then reality struck. Having the huts was one thing. Getting them across oceans was another. Erecting them under fire was something else entirely. The average Quonset kit weighed far more than the British equivalent. The larger panels demanded more space in cargo holds. And the mixed-use interior options meant crews had to sort parts carefully before they could even begin assembling. The United States had successfully created a shelter for global war, but they had not reproduced the speed of the British system. The difference would become obvious once both nations started putting their huts up under wartime conditions, because when the steel hit the mud, the Nissen worked like a reflex. The Quonset still required thought. From a distance, a Nissen hut and a Quonset hut look almost identical. A curved steel shell, wooden end walls, a long half-barrel silhouette rising from the earth like a steel wave. But move closer, and the differences reveal themselves not just in shape but in philosophy. A British engineer in 1941 could walk up to a Nissen hut and instantly understand its anatomy. It was a framed structure. The shape came from a sequence of simple, identical steel ribs set into base plates. Corrugated sheets were then bolted onto those ribs like armor on a skeleton. The steel skin didn't carry. The load the ribs did. This meant the sheets could be thin, light, and incredibly easy to transport. It also meant damaged sheets could be replaced with almost anything: spare roofing, scavenged corrugate, even flattened fuel drums. The structure stayed standing because its strength lived in the frame. The Americans chose a different route. The Quonset hut relied on a stressed skin system where the curved panels were designed to act as part of the structure itself. Instead of many small ribs, Quonsets used deeper, heavier ribs, combined with large, heavy-gauge steel sheets that carried some of the hut's load. This made the hut incredibly tough, better in hurricanes, better in the Pacific, better against heavy winds. But it also meant that if even one of those big panels was dented in transit or crushed by cargo, handling the assembly slowed or stalled until crews found a replacement. The differences didn't end there. British huts had modular end walls that could be built from local material: timber, brick, stone, even sandbags piled into a semicircle. Whatever a construction crew had on hand could close the ends. In a war where supply ships were torpedoed weekly, that kind of improvisation wasn't optional, it was survival. The American Quonset hut had standardized end wall kits shipped with the hut. Good for consistency. Not always good for speed. If a crate went missing, or if the wood warped in Pacific humidity, a crew could find itself wrestling with parts that wouldn't fit without major work. Ventilation was also handled differently. The Nissen relied on vents built into the end panels and small ridge openings, simple, rugged, almost impossible to break. Quonsets added adjustable louvers, optional insulation panels, and interior lining. Comfort improved. Complexity increased. Then there was the question of tools. A Nissen hut could be erected with basic hand tools: spanners, hammers, rope ladders. A Quonset hut preferred more precise tools, especially for heavy panels and interior fittings. In frontline conditions that slowed teams down, none of these differences made the Quonset a bad design. Far from it, it was durable, adaptable, and capable of serving in climates the British never had to consider. But when judged purely by assembly speed, the engineering details mattered. Britain had built a shelter optimized for one thing: rapid deployment across Europe by soldiers under constant pressure. America had built one optimized for global deployment, long-term use, and industrial uniformity. Two brilliant answers to two different problems. But only one of them could be assembled before sunrise on a battlefield drenched in rain. Speed on the battlefield doesn't start when the first bolt is tightened. It starts months earlier in the factory, in the shipping yard, and in the long, vulnerable chain that carries steel from a mill to a distant war zone. Britain understood this early. By the time the Second World War erupted, the Nissen system had been shaped by two realities: shortages and proximity. Britain didn't have endless raw materials. It didn't have room for excess. It didn't have the luxury of shipping heavy construction components across oceans. So it designed a hut whose production relied on thin, corrugated sheets that almost any steelworks could stamp, small ribs, easy to fabricate on simple dies, standardized parts that could be made in multiple Commonwealth factories, and lightweight bundles that fit neatly in today, rail cars, lorries, and shallow-deck ships. This kept supply lines tight, predictable, and efficient. A Nissen hut could be broken into dozens of compact bundles. If one box went missing, the rest of the hut could still be built with minimal improvisation. And if Britain needed an emergency run of parts, local factories could tool up without massive reconfiguration. America's situation, and therefore its design, was very different. The United States fought a global war. It needed huts in Iceland, Panama, North Africa, Australia, the Solomon Islands, the Aleutian Chain, and dozens of Pacific atolls barely big enough to hold an airstrip. The U.S. supply network was a miracle of scale, but with scale came weight, distance, and complexity. The Quonset hut reflected that complexity. Its heavy-gauge steel sheets required large, specialized presses. Only certain factories could make them, which meant production was centralized. The curved panels were longer and bulkier than Nissen sheets, so far fewer of them fit into the hold of a Liberty ship. Where a British transport might load 20 complete Nissen kits, an American transport might only carry a small handful of full Quonset shipments. The Americans compensated with staggering volume. By the end of the war, more than 150,000 Quonset huts had been produced. But producing a thing is not the same as delivering it, and delivering is not the same as assembling. A hut sitting in a stateside warehouse was worthless to a marine landing on a beach in the Solomons. And because Quonset parts were larger, heavier, and more prone to damage when mishandled, logistics units had to exercise more caution. A dent in a Nissen sheet was a shrug. A dent in a Quonset panel could halt construction. Then there was packaging. Nissen components were typically sorted into numbered bundles that could be laid out quickly. Quonset crates often mixed interior panels, insulation end-wall parts, and steel ribs together for shipping efficiency, but at the cost of valuable time during on-site sorting. This wasn't incompetence. It was the unavoidable consequence of supplying a war fought across half the planet. And so in practice, the British had an enormous advantage: shorter supply lines, lighter materials, and a design shaped by 2 decades of fine-tuning. The Americans, meanwhile, had created a hut that excelled in durability and versatility, but sacrificed speed in the process. Field crews felt the difference most sharply when they tried to assemble these structures under harsh conditions, and nowhere was that contrast clearer than on the front lines of the war itself. The battlefield is the ultimate judge of engineering claims. Blueprints don't fight weather. Manuals don't stand in knee-deep mud. Production charts don't help when a sudden gust of wind rips a steel sheet out of a man's hands, and this is where the real-world divide between the Nissen and the Quonset became unmistakable. British engineers had a saying during the war: if you can carry it, you can build it. The Nissen hut's light components meant a 6-man squad could carry every single piece by hand. No cranes. No trucks needed after unloading. Men could walk ribs into place, brace them with temporary poles, and begin sheeting the roof within minutes. On calm days, a hut could rise startlingly fast. On windy days, it took more muscle, but still no special equipment. Where the Nissen really shined was improvisation. If one sheet was bent, men flattened it with their boots. If end-wall timber was missing, they scavenged farm planks or ripped doors off ruined buildings. If the ground was uneven, they dug in the base plates with entrenching tools. If snow piled high, they reinforced the arch with whatever wood they could find. The hut's simplicity made it naturally flexible. It tolerated mistakes. It forgave damage. It welcomed improvisation. And on a war-torn continent like Europe, that flexibility saved hours. The Quonset hut, by contrast, was a creation of American abundance, and abundance sometimes cost time where scarcity created speed. Those large, deep corrugated American panels were robust, but they were also unwieldy. 2 or even 3 men often had to coordinate to lift and position them. In windy Pacific weather, they behaved like sails pulling crews off balance. Bent panels didn't always fit back into the stressed skin curve, which meant construction stalled until a replacement arrived or until someone reshaped it with a mallet and prayer. Then came the insulation. In Alaska or Iceland, it was a blessing. In the South Pacific, it was a complication. Interior liners had to be aligned, vapor barriers tacked in, holes matched precisely. Each of these steps added minutes that the British didn't have to spend. And because the Quonset was meant to serve as everything from hospitals to radio shacks, its various models had different interior arrangements, door frames and end wall kits. A crew familiar with one model might find itself slowing down when assigned to another. The Nissen had almost no variation. Uniformity was its strength. Familiarity became speed. Another battlefield difference was foundation choice. The British often placed Nissens on simple sleepers or directly on the earth. Fast, minimal preparation. Americans, wanting a sturdier long-term footprint, sometimes used wooden floors or raised foundations. Better comfort, yes, but slower. Climate also played its part. In Europe's cold rain, the Nissen's thin sheets warmed quickly once troops lit stoves inside. In the tropics, the Quonset's heavier walls absorbed heat during the day, turning the interior into a steel oven until proper ventilation was cut in. Yet despite these challenges, Quonset huts were admired for their durability once completed. They resisted storms that shredded tents. They protected radios and medical gear from jungle rot. They survived typhoons. But the question at hand isn't durability or long-term comfort, it's speed. In field after field, from France to Burma to North Africa, the same pattern appeared. Britain could erect more shelters more quickly. America could erect stronger shelters, but not as fast. The final piece of the puzzle, and perhaps the most important, had nothing to do with steel or supply chains at all. It had to do with people. Even the best steel is nothing without hands to raise it. And in this, the human, the factor, became the final arbiter of speed between the Nissen and Quonset. The British Army's Royal Engineers had decades of experience raising Nissen huts under combat conditions. Entire manuals were dedicated to the task. Soldiers drilled repeatedly, and crews became almost instinctive in their work. One officer recalled that his squad could erect a hut blindfolded in the rain, not literally, but the metaphor captured the rhythm and muscle memory honed through constant repetition. Teams were organized to the letter. One man held the rib, another bolted the base, a third ran sheets along the curve, and others secured end walls. Every movement was choreographed. And when improvisation was needed, say a bent sheet or uneven ground, soldiers knew exactly how to adapt without slowing the project. Speed had become second nature. The Americans faced a different reality. The Quonset hut was new. Crews, often Seabees or Navy construction battalions, were brilliant at many things. Port repair, airfield construction and heavy engineering. But raising a Quonset hut wasn't instinctive. Every variation in model or site required reading the manual, measuring, adjusting. Mistakes could cost hours. Furthermore, American crews were spread across the globe. Training varied from base to base. Some teams had months of practice. Others received a quick demonstration, then were shipped to a remote island where winds, rain, and coral-strewn soil made even lifting a panel a challenge. Standardization helped, but nowhere near the seamless experience the British enjoyed with Nissens in Europe. Doctrine mattered too. Britain had a culture of rapid assembly. Every officer, corporal and private, knew that a hut delayed by even 1 hour could mean more casualties in winter, more exposure to bombing, more logistical strain. Time was always the enemy. Training tools and organization were all tuned to shave minutes. The Americans prioritized global durability and adaptability, which sometimes slowed procedures. The Quonset was designed to be versatile enough for a typhoon or a frozen tundra, but that versatility demanded attention and care during assembly. The difference was subtle yet constant. Where the British crews built instinctively, American crews built thoughtfully. At the end of the day, both nations produced huts that saved lives, stored equipment, and facilitated operations. But the combination of trained hands, standardized parts, improvisational flexibility, and a culture of speed made the Nissen hut faster to erect on the European front. It wasn't superior steel or American inexperience or design flaws. It was the quiet power of repetition doctrine and human instinct intertwined with a design optimized for war on Britain's doorstep. By the time the last battles of Europe drew near in May 1945, the Nissen hut had proven itself not just as a shelter, but as a symbol of efficiency in war. Its simplicity, flexibility, and the accumulated experience of decades allowed Britain to raise entire camps, overnight supply hospitals in hours, and give soldiers the comfort of a roof when the front was chaotic. The Quonset hut, meanwhile, became an emblem of American industrial might. Durable, adaptable, and globally deployable, it served across oceans, climates, and campaigns, proving that mass production could meet the demands of a world at war. But it never quite matched the speed of its British cousin, a difference born not from steel or engineering, but from experience, doctrine, and the relentless pressure of wartime necessity. Two cousins of steel. Two answers to two different wars, both brilliant, both vital, and both a reminder that in war, the fastest solution is often the one tempered by time, practice, and human ingenuity. The Nissen hut and Quonset hut still stand today in museums, abandoned fields, and even some military bases, whispering stories of the soldiers who built them, the engineers who designed them, and the quiet competitions of speed, skill, and survival that defined a world at war.